Okay, folks, let's just have a quick look at 1 minute papers from last time. So somebody asks, what exactly is it that the rewrite keyword does? And your wish is my command. I shall show you how with and rewrite work in this lecture. So someone says how to better hunt down where your program does not give enough information and techniques how to go about solving that. I think we'll probably see quite a lot of that. Yeah, and also the suggestion, let's try to build some sort of index for what's discussed in the lectures that's slightly more informative than the title. As ever, let's crowdsource that. Pull requests welcome from people in the room and people out there or in YouTube land. Okay, dot patterns, that caused a bit of worry. I'll try and get back to that as well. Somebody asks, why was m greater than or equal to n an argument in vector take? Okay, well let's have a look. We're trying to put m elements in and get the first n elements out. And remember, to make a vector of length n, we actually have to give exactly n elements. So we better make sure that there are enough elements that we can take the first n. That's to say, we better make sure that we know that m is at least n. So we've got at least n coming in order to take the first n out. And pretty much the use we make of it is to get rid of the bad case, where we run out of inputs, but we're still asked for outputs. That's where we use the proof to say, go away to that situation.
So that's a bit like how you used key before, right?
Yeah.
Okay.
Yeah.
That was
So where in Haskell you might give back an empty list at that point, and then it would be shorter than you expected, or you might cause an error, or you might have to use a maybe or something like that. Here, if somebody makes us a nice promise on the input, we can keep the promise to give back exactly n. So we're just working slightly more tightly. Right, so for problems with the vectors, would it be possible to use actual vectors with values to show why the code works? Yes, sometimes I need to remember that this sort of strange idea persists that watching something running on an example is more confidence inspiring than seeing a program check with a precise type. It's a funny thing, but yeah, we can do that. There's some kind of, I'm terribly used to reading the program and believing it, rather than running a program and believing it. But I'm happy to do that example. In fact, how about we do one now? So let's just type in an expression. Maybe to make it big enough, I'll do an example. So let's do vtake, and let's say we've got 5 coming in, 3 coming out. We'll have a question mark for the proof. Sorry, let me get this right. The type is going to be, we're going to have a vector of 3 natural numbers, and we're going to make it by taking the first 3 out of 5 from the vector 1, 2, 3, 4, 5. Yeah? What's it whinging about? Oh, I've forgotten why I write comma minus instead of minus comma. Right, it's comma minus because the long bit comes afterwards. Right, so in order to justify that this is an okay operation, I have to give a proof that 5 is greater than or equal to 3. But fortunately for me, that type computes all the way down to the unit type. 5 greater than or equal to 3. Evidence for 5 greater than or equal to 3 is evidence that 4 is greater than or equal to 2, is evidence that 3 is greater than or equal to 1, is evidence that 2 is greater than or equal to 0, is trivial. Right. Yeah.
What shortcut did you go just to go from the overall goal to just shorten it down there?
So I do Control-C, Control-comma to show the goal.
Right.
And then I can give the trivial proof, now that we know that that's of unit type. And then if I ask it to normalize example, it will just give us 1, 2, 3. Okay?
So why does M need to be an explicit argument to does it?
Well, yeah, so there's an interesting question here, which is a design question of which of these in practice would we need to give explicitly and which not. We certainly need to pattern match on them when we're writing the program, but that doesn't mean that we necessarily need to give them explicitly at use sites.
Because it's already implicit in the vector, isn't it? In the first vector.
Right. So we can see we could try refactoring it. What I'll do is I'll make those implicit, and I'll just do a bunch of commenting out. Well, I can't do this with commenting out. I have to do this with the manual override, because we do need to look at them. And then hopefully I can just comment these ones out, and hopefully I can just comment those two out. And oh, it doesn't like. Well, further down, what I'll do is I need to load my comedy file. What's it? What do I do? It should be easy to do that. I'm not winning. I'll just comment out the boring way. Right. So as it happens, that worked out for us. One good thing which we'll get to just by way of building instincts about what's likely to work and what's not. It's good to learn the difference between what are sometimes called rigid symbols and which things are not rigid. Basically, constructors, whether they are value constructors or type constructors, are rigid. And what does that mean? That means if you're trying to tell if two uses of those constructors match each other, you can compare them component-wise. So this says the only thing that's going to match vec something something is vec something something. Because rigid symbols have no defined computational meaning. They are what they are. Whereas something like greater than or equal to, this can compute in various ways. So if you're matching x greater than or equal to y against 5 greater than or equal to 3, that doesn't mean that x is 5 and y is 3. Yeah?
So now that you commented 5 and 3, what does the example do then?
Yep, fine. Yep. What's going on here? Why? Oh, because I'm forgetting how to use actor, that's fine. Load file, Control-C, Control-N, example.
But we could still make greater than or equal to an implicit.
Right, so it's an interesting question about whether we can make the proof implicit. And that's
make using it harder, wouldn't it?
it's an interesting thing to try to do. Well, watch this. It's good to explore this. I'm willing to be derailed by this for slightly longer. So we we don't comment it out, we make it implicit. To make it implicit, the funny thing is you have to give it an empty, some sort of name to make it implicit, to put it in curly braces. But then we need here to do this, because we do need to see it in order to say it's nonsense.
We don't need it in the first case though, do we?
We shouldn't do, so we could just leave it out. But let's see what happens. Comment that out. Right. So some things work and some things don't. You can see that when we said vtake here and we didn't give this argument explicitly, it wasn't able to figure it out. There's no constraint that forces that proof to be this thing in particular. So we're going to have to give this one implicitly. Oh, right, sorry, give this one explicitly. We're going to have to use the manual override if we want the proof to be implicit. In a concrete example, where we've got two actual numbers, 5 and 3, and the type of the greater than or equal to computes all the way down to 1, it's perfectly happy to infer that this is the proof. Why is that? Because when Agda tries to infer a missing element of a record type, it does it by trying to infer each of the fields. And of course, there are no fields in the unit type, in the one type, so it's very easy to infer all the fields. So, yeah?
So if we had 6 instead of 3 there and we kept the proof, would you just understand that what the proof that we gave it is wrong?
Well, if we give 6 here, let's think about what's right. So we give, if we give 6 explicitly.
Sorry, 3. So vec not 6, like in the.
Oh, right, in the type.
Yeah.
Well, there it will complain. Yes, here it's saying that it's trying to take 6 elements from 5. The type 5 is greater than or equal to 6, computes all the way down to the 0 type, that's to say it's impossible, and now it's complaining that it doesn't know a proof of the 0 type. And if we try and run that, it'll get quite far, it'll take the first 5, and then I'm saying, I'm now stuck on how to take the last one. So only bites when the countdown reaches 0. So generally speaking, I would make that proof explicit. Here's a different way to cut it. Just so you know, you've seen how to do the manual override with putting things in curly braces.
Missed one of the curly braces on
On that one, yeah. And then here I'll need to put those back in. And now I need to put that back to being 3. Okay. Right. So you know that if there's something that's usually implicit, but you want to be explicit about it, you use curly braces. What happens if there's something that's usually explicit, but you want to tell Agda to go figure it out? Well, that's where you use an underscore in an expression. So I can use an underscore here to say, you figure that out. If it can't figure it out, it'll turn yellow and pretty soon tell you, I don't know what that is. But as it's looking for an element of the one type, it does know what it is. Okay, I'm tempted to put this back the way it was so that I don't have to fix up the rest of my file. But there we are. Tell you what. I better fix those up.
But you could replace those with underscores as well.
That's exactly what I was about to do. And indeed, if I wanted to, I could replace those two with underscores. But actually I don't want to, because I think it's slightly clearer not to. Right, in particular, we can see here that stuff is getting smaller. So that's a good documentation of why this program terminates. Okay, we can also see the vectors getting smaller, so maybe it doesn't matter. All right. Now, I don't know what went wrong with my other bits and pieces, but okay, they're working now. Oh, I know what went wrong. I need to do that. Right. So the next thing I want to do is prove two important equations. One of which says, well, basically you can think of vector take as a way of turning a greater than or equal to proof into a vector operation. So if you think of it in that higher order way, in comes a proof about numbers, out comes an operation on vectors. And then what we're saying here is that if we put in the reflexivity proof about numbers, out comes the identity operation on vectors. And if we put in two greater than or equal to proofs stuck together with transitivity, we get out two operations on vectors stuck together with composition. So doing the whole take in one go is the same as doing the take in two stages. So do nothing turns into do nothing, do this then that turns into do this then do that. Okay? Let's get cracking. Here, it makes sense. Well, we're trying to prove an equation. We can ask ourselves the usual thing we ask, which is, why is it stuck? Right. Why isn't the left-hand side already equal to the right-hand side? Because VTake is stuck. Okay? How do we get it unstuck? We need to think, what does VTake pattern match on? It pattern matches on this number first, n. So if we look at n, something will happen. Okay. So we're in a special case. We need to prove that nil is equal to x's. We already know that if we're taking no things, we give back the empty vector. So we've got the empty vector on the left-hand side. We've still got x's on the right-hand side, but we know that x's has length 0. So what's going to happen when we pattern match on x's?
It's always going to be.
We'll just get a nil case. So let's just ask very carefully, what's going on? We are checking out the constructors of vector against the type of the pattern variable that we had. So let's just look again.
Yeah, you need to properly reload.
Yeah. Why is it giving me that? I did reload.
Now you need to kill that dummy.
No, I'm fine. Back in the room. Right. The thing we're looking at has a 0 here, and the constructors have nil. The nil constructor has a 0 in this place, whereas the cons constructor has a successor in the length place. So the thing is that because 0 and successor are constructors, they are rigid, and the thing that you know about rigid symbols is that they match each other and they don't match different rigid symbols. So 0 is not successor. The whole point of giving different constructors to a data type is to make different things. So Agda knows that 0 and successor cannot be the same, and it knows that any constructor used to make x's has to have this type. So the only way this can be made with a constructor is if it's the nil constructor. So Agda's doing equation solving on the indices in order to figure out which constructors are possible. So that's that's a bit of background work that saves us a lot of trouble. Okay, so now we're in the lucky position where we can say that's reflexivity. Well, I need to say, hang on, I'll do control C, control A. Yes, I forget. Reflexivity in this locally takes an argument. So that's just reflexivity of the empty vector.
Can you do it that, you know, you did control C to change the XS into the empty vector. Can you just do control C, control A from the very start? And it can change the input as well to it?
So control C, control A by default doesn't do any pattern matching. So it says, can I build up the right hand side now? But it doesn't do anything clever about trying to figure out what pattern matching would be good to do. Yeah.
So the proof that you are passing in VTake, what's that one? Like with the briefly and then the dash arrow equal n?
So what?
The proof that you are passing in VTake.
This thing?
Yes, yes.
Oh, that was defined in the previous file. It's Agda. Right. So somewhere here we define these things, proving that greater than or equal to is reflexive and transitive. So you'll see up at the top there's open import lec 1 done. That's to say all the lecture 1 stuff. Bring it in and unpack that module. Okay.
We don't need the pattern match on X's, do we? And we just return the empty.
Well, careful. Right, so the question is, can we just say refl here? And it says, no, you can't, because nil is not the very same thing as x's. Now, we happen to know that there's only one constructor x's can possibly be, but because vectors are a data type, Agda's not going to think that through for us. Actually, this is the answer to one of the questions that came up much earlier, but we're now in a position to answer it, but what the difference is between records and data types is that Agda is much more aggressive when it knows something is a record. So we saw a moment ago that when we wanted an element of type 1, that's a record type, Agda was happy to say, I just know what that is, because it tries to figure out what it is field by field. Whereas when we're trying to figure out something of a data type, you and I know that there's only one thing that's a vector of length 0. But because it's a data type, not a record type, Agda is too scared to say, oh, I know x's has to be nil. So we have to point out by pattern matching that there's only one thing it could possibly be. So that's why when you can make something a record type, it's often a good idea to do so. Is because Agda will solve problems more aggressively when it knows things are record types. Okay. Looking at the step case, we've got 2 successors, which is nice. We don't have a 0 on the input size. Let's look at the vector. And then we are in the usual sort of situation. We can see that we have that both sides have managed to send the first element, x, out the front, and then in the back, we're ready to use our induction hypothesis. Okay, so we've got lots of options, and let's work backwards gently to see what's actually going on. So we could start by saying rewrite v take id fact n x's. And there we go, with one bound we are free. You could see, let me just, if you look at the goal, you can see that this expression, this sub-expression here, is the left-hand side of what we get when we call v take id fact on n and x's. And rewriting it to x's is exactly what we want to do. So that rewrite will do the job.
So rewrite only works with equality proofs.
Yes! So we saw that work. Let's instead work slightly more slowly, and instead of using rewrite, use with. Now what just happened? Remember, with just means, so, okay, the left-hand side of a program, when you're pattern matching, that's where you see stuff. And then on the right-hand side, that's where you say what something is. So you say, when I see this input, I know the output is that. That's pattern matching. And what with does is it says, I would like also to be able to see the result of this. I think that would be a useful thing to look at. Yeah? So all that's happened is I've said with, I've given my recursive call, I've added an extra column with a pattern variable q, and now in the goal we have this extra q that tells us this equation. Yeah? Now, if I pattern match on that proof Q, what's going to happen? Well, we know that the only constructor of equality is REFL, and that requires both sides to be the same. So the only way REFL can make Q is if x's is equal to this thing. And actually I can see this is going to go horribly wrong, potentially. Haha, it's refusing to pattern match on Q because it can't see why the two sides of the equation are the same, and it's worried that the two sides of the equation might not be the same because x's occurs in the left-hand side. So it thinks I might be trying to make some kind of infinite loop by doing this. So it's not letting me. That's a nuisance. Fortunately, well, remember what happened also. When we did the rewrite, we got x's on both sides. So the only reason why this could be REFL is if x's is this thing. If that had worked at all, sorry, yeah.
Could we use like the equal $equal to help us get x inside here and here?
Yeah, we could certainly do that. That's another way of doing it. That's probably the way I would habitually do it, but I'm trying to show what's going on with rewrite. Okay, so let's hang fire a moment. Stick the question mark back there, comment that out. Comment that out. Okay, so we're back where we were. So with says, I'd like to see this extra stuff. One thing I can do, I can say instead, with, and I can just grab this lump of stuff that I'm interested in out of the goal, put it here, and see what happens. Now, something quite funny happened there. Where this thing used to be in the goal, there's now a Z. So what happens when you do with is, as well as giving you an extra column with the value of that expression, it abstracts all occurrences of that expression from types, in particular from the goal, and it turns it into a variable. That's where that Z came from. That's the result of the expression, and it's replaced the original thing in the goal with the Z. So this now has Z where it used to have this thing. And that means if we pattern match on Z, for example, the goal will compute accordingly. But that's not what I want to do, because the problem here is I know Z, I know the result of that thing, but I don't know any facts about Z. Now let's see what happens if I do two widths at once. Our goal, so the Z corresponds to this thing, and the Q corresponds to that thing. So the Z is now the tail on the left-hand side of the goal, but let's have a look at the type of Q. That's a handy fact about Z. Remember, the type of this thing has this thing on its left-hand side. So when we turn this thing into a variable, Z, that includes the Z in the type of this thing. So now we've got our Z that corresponds to the left-hand side of the equation, and we've got Q with Z on the left-hand side. And now we can pattern match on Q. And something nice happens. Let's just undo that. Look again. Why does it never undo when I want it to undo today? Look, Q says Z equals X's. We want to say, how can that be made by a constructor? It can be made by a constructor REFL, but only under the circumstances when Z and X's are actually the same thing. So in order to give us a REFL pattern, it has to make Z and X's the same thing. That's the only way that can possibly happen. So when I do that, it says, where you had Z before, you now have dot X's. The dot means I'm telling you, not I'm asking. It's saying, the only thing that can go here is that X's. And the reason that's the only thing that can go there is because this constructor is REFL. So what's going on in general is, well, remember last time I said pattern match on an equality proof with a variable on one side. Well, okay, the variable has to not occur on the other side, which is why we got stuffed last time. But this way, it's always going to work. So what happens is So rewrite is just a handy notation for abstract the left-hand side of the equation using with, abstract the proof of the equation using with. Just what we had here. This is the left-hand side, this is the proof of the equation itself, and that's always going to give us some equality proof with a variable on the left-hand side that we can then pattern match on to get the rewrite. Do you want to see it again? Yeah. So let's just do that again in slow motion. So we were here. Let me just grab this thing. This is the induction hypothesis. Right. So the induction hypothesis has this lump of stuff on the left-hand side. And this lump of stuff also occurs in the goal. So if we do that double with, well, if I do this with first, that'll just give me a proof. You can see I get my extra proof Q with that thing on the left-hand side. But now if I also with the left-hand side, you can see here, right, this lump that I've got highlighted, this recursive call to vtake, occurs in the type of Q and it occurs in the goal. So now when I use with on it, both of those get turned into a variable. You can see we have our new variable z, and it shows up both on the left-hand side of Q, of the type of Q, and in the goal. So we've turned it into a variable in both places. And now we've got an equation where, as it happens, both sides are variables. But certainly, we know the left-hand side is a variable because we just deliberately made it one by choosing exactly the right thing to put a variable on the left-hand side of the equation. So now when we pattern match, we get to here, and we win. So that's what's going on. Rewrite is syntactic sugar for doing a double with on the left-hand side of an equation and the proof of an equation, the proof of the equation. Then pattern matching on the proof in order to force the variable to get substituted by the right-hand side. So rewrite really works in two stages. Turn the left-hand side into a variable and then do a pattern match that turns the variable into the right-hand side. So it's so that's the kind of sort of more slowly, this is rewrite in slow motion, if you like. Okay. I'm going to jump over the composition fact just because time is short, and I want to show you one more thing if I can. I don't know if I'll get all the way there, but let's see. Here I'm using Agda's mix-fix operators to hopefully be a bit suggestive in the syntax. This is a lot like the less than or equal to thing that you've got in exercise 1, except it's double-sided. So what is this? This is a type indexed by 3 numbers, and the idea is that we are sharing the number in the middle out between the two sides. So we've got a constructor that's that I've called zzz, which says if we're sharing 0 out, we're definitely having 0 on both sides. And then I've got two constructors, left and right, which say, if you already know how to share out m things, and then somebody gives you an extra thing, you can give it to the left-hand side. But in that case, you're not giving it to the right-hand side. Whereas the other constructor, RRR, talk like a pirate day, if you're already sharing out m things and somebody gives you one more, you can give it to the right-hand side. But then definitely not to the left. Okay? So this basically says we're building up a number from two other numbers by taking successors from left and right, but not necessarily like adding all of the successors from the left, then all of the successors from the right. We're being careful about what's coming from where. And what this tells us how to do is to interleave two vectors. So this program here says, well, if we know how to share m out as L and R, and we want to build up a vector that's m long, we can take some of the elements from a vector on the left that's L in length, and some of the elements for a vector on the right that's R in length, and we know we'll definitely have enough to fill the whole M. So think about, when you are doing that riffle shuffle for poker, you've got a pack of cards cut into some on the left and some on the right, and you know that the total adds up to 52, and then you kind of whiz them together with your thumbs, and they interleave in some order. Well, these are like the instructions for doing that interleaving. You can think of RRR as saying, take the next one from the right.
So the L and R always sum to n.
Yes, these you can see that we start off with these two adding up to the middle, and then at each step, if they added up to the middle before,
Yep.
they'll still do. So that's a good thing to prove, actually. Right, so let's have a look at this thing. We need to look at our instructions. So so this one, we've got the 0 sharing. And that means all the vectors in sight must be of length 0. So if we just pattern match gratuitously in order, for documentation purposes mostly, you can see we're building a 0 length vector from two 0 length vectors. Whereas here, this says take from the left. And you can see that the left vector's definitely got something to take. So we can look at it, and then guess what? It can just figure out what to do there, because there's only one way to put the jigsaw together. Similarly here, if the instructions say take from the right, you can see that the right vector definitely has something to take, so we can pattern match on it, and again, we're done. So you can see we're just following the instructions for putting the whole vector together from the two vectors on either side, given that we know that they must have exactly the right amount of stuff in them. And then I think I get to leave this as a cliffhanger. Here's a trick we often do. Suppose I want to invert this operation. Suppose I've got a way of sharing out m things as L on the left and R on the right. And somebody gives me a vector of m things. Can I divide them out into a vector of length L and a vector of length R. So instead of riffling the two vectors together, can I deal them out apart according to the instructions? You can think of these things as instructions for dealing as well. You know, one to the right, one to the left, we're done. Yeah? However, given that L and R add up to M, there might be lots of different ways we could deal out M things as L things and R things. So we might, for example, deal the first L things to the left and the last R things to the right, even if our dealing instructions don't say that. So what we would like to be sure of is that when we deal the vector out, we get back the two vectors that would riffle together to make what we started with. So we want to know that dealing out is the same as is riffling backwards. We don't just get any old rubbish, that we get back the things that behave properly. So here's how we do that. We define a data type that characterizes the properties of vectors we would like. So if we've got a vector of length m, and we know how to deal m apart into L and R, we would like there to exist a vector on the left and a vector on the right, such that the vector we first thought of has to be this interleaving, this riffling. Yeah? So the only way we can give a constructor in find split is if we are sure that we've chosen the correct two vectors that interleave correctly, or that interleave to make the vector that we're looking for. So just as the only way, the only way we can make a vector of length 5 is to choose vector cons, the only way we can make a find split of a given vector is to find the right x left and x right. Find the correct x left and x right. So that's to say, the next goal tells us something important. It says, but it is the case that for every vector x's, we can indeed find that split. So the question is, can we write this program which will exhibit XL and XR that are guaranteed to fit together in the right way? And what happens when we do? Ooh, I've got 4 minutes. I've got enough time to do it. Okay. So let's see what our situation is. We've got to find the split of NNN and X's. So what we'll do is look at the instructions. Okay. In this case, everything's 0. The vector that we're trying to split is 0. So now we have to show that we can find a correct splitting of the empty vector. We have to give the left vector and the right vector that fit together properly. Can you guess what the left vector and the right vector are going to be, given that we're trying to make the empty vector?
The empty vector.
They're both going to be the empty vector. Okay. Meanwhile here, we know that we've got a non-empty vector to split, so we can pattern match on it, and we will get only a cons case. So, now what do we need to do? We've got our first element, and we know it ought to come from the left. But we need to worry about the rest of the elements. Well, we need to make a recursive call, but we can't just give a recursive call. That's not going to be the right type for the answer. I can say find split n x's, and you can see the recursive call will give me this thing, but we need a slightly extended thing. Okay? Well, but it's probably going to be useful information, this recursive call, right? So we might as well with it and see what happens.
Can we rewrite it?
No, because it's not a proof of an equation. But we can grab it and see what it tells us. Okay, so I've grabbed it. You can see I now have a Z of type find split this thing. Well, now I pattern match on Z. And I can see a constructor split bits with the left and right vectors that made up x's. But I can also see here that x's is the very thing made by interleaving those two. So this is showing me in the pattern that my original vector, the tail of the original vector is made the way I want it to be made. We can just see it right there. And now, oh, it's being done. I can give back split bits, and that's going to be, it's too stupid. I can give back that indeed the x came from the left component. And I'd better stop there, but you can imagine what's going to happen on the right hand side. The message here is that not only do dot patterns arise as the result of, like, this is the only thing it could possibly be. We sometimes use that deliberately to invent new ways of seeing. What we're really saying here is we would like to see vectors as being made by interleaving. And what this thing says is it characterizes which vectors can be seen as interleavings. And now we are proving that, in fact, all vectors can be seen as interleavings, so that when we make a recursive call, we see the tail of the vector as an interleaving. So one thing we can do, you couldn't really do this in Haskell terribly easily, is to program more interesting ways to look at your input. You know, funny new kinds of pattern matching that are made by computing stuff in an interesting way. Now we can do that. Okay, I will stop there.